Welcome back. This is Math 111, section 10.2, page 3. There's two different methods for determining if a result is statistically significant. This video will show the classical approach. In the classical approach, we're going to compare these z-scores. So you need to have your z-table ready. We're going to compare the critical values, or the z-score that defines the critical region, to the z-score for your point estimate obtained from the sample. That one's going to be called the test statistic, what we're going to compare it to. Using the classical approach, test the hypothesis of a given significance level. This is a one-tailed test. We're only testing the the right-tailed test right over here, finding these p-values that live in this zone or not. So let's check it out. There are 200 values and 75. The significance level for these things is 0.05. For a right-tailed test with a z-score of 0.05, that means 95% of the area is to the left and only 5% of the area is to the right. We look up 0.095 in our z-table. We have to reverse look up this 0.095. 0.095, man. When we look this up, we're going to get 1.64 and then 1.65 and then halfway between. You can use either value. The book or the author of this chose to pick the value right in the middle. Not always necessary, okay? So when you're taking your test on Friday, I'll take all those things into consideration. All you have to do is be close. Here we go. This Z value that we're going to compare to this critical region is used with this formula. To find your testing Z value, or the test statistic Z sub 0, you need to take X over N, pre-calculated right there, minus P all over. Make sure that you use parentheses properly, or do this in multiple steps. P minus 1 over N. So that's where all these data values come from. That's the formula to get the test statistic. Since this test statistic was 2.314, again, they rounded to the nearest thousandth, and we'll probably round to the nearest tenth for these Z values, is greater than 1.645, we reject the null hypothesis. Let's do a two-tailed problem. A two-tailed problem means we could have area to the right or to the left. And so our data values could fall into either one of those zones. First, we have to check and make sure that this thing is greater than 10. It pretty much will always be. For a two-tailed test, we have to take this alpha value and divide it into two sections. This means that 1% of the data is shared with the right tail and the left tail. If 1% is shared, then that 0.5% is to either side. So changing 0.5% into a decimal is 0.005. Our Z table looks up area to the left, so we're looking up an area to the left of 0.005. When we do that, again, over here, we get a negative value. It could be negative 2.57 or negative 2.58. They're both equidistant on either side. So in your computations, rounded to the nearest hundredth, you could use either of those data values. I'm not sure exactly where. They must have had a more sophisticated chart than we do, where they got this 2.57 and then halfway between value, but we're going to round those things to the nearest hundredth on your test. Okay, the two tails are given. You'll have one z-value, the negative one right here, and one z-value, the positive one right there. I hope that makes sense. Then, to get our test statistic, or z sub 0, we use this formula up here again, x over n minus the p-value in question divided by the square root of all of this. We get 1.291. Since this z-value lives inside that zone, or in this white space in between, we fail to reject the null hypothesis. It's different than just accepting the null hypothesis. We actually fail to reject it. It is statistically significant. Well, I'll talk to you soon, guys. If you have any questions, just shoot me an email. We will see you later. Bye.